This is Veder Gamans from Software for Chemistry and Materials. Let's have a look at how we can use the Graphical User Interface of the Amsterdam Modeling Suite to build simple linear polymers. And we'll start with ADF, which is our molecular DFT code, to build the monomer part of our structure. We'll take one carbon atom, press 2 to create a double bond to get another carbon atom, and then select the whole molecule, which is done by Command M or Control M on a Windows machine, and press Command E to hydrogenate the system. So in polyacetylene we'll have this as a unit, and this carbon atom will be connected to the next carbon atom of the same system, but sitting exactly next to it, so infinitely repeated into this one dimension. So I want to remove these two atoms, and then we can imagine that we can start building a zigzag structure of this polyacetylene across this one dimension here. In order to be able to deal with this infinite repetition of the unit in 1D, in this case, we want to switch to a module that can deal with periodic boundary conditions, so we'll use DFTB in this case. We'll switch from ADF to DFTB, and there by default, we will remember we were dealing with a molecule, a 0 periodic system, 0D periodic system, and we want to change that to 1D, a chain. So 1D system can be a linear polymer chain, can be a carbon nanotube, and that system is repeated in one and only one dimension. And this little red line here, that is the lattice vector, so in this case that is the direction in which a system is repeated infinitely. Now we want to drag our monomeric system, or the system that's repeated infinitely, sort of close to the line. We'll try and get a little bit in a better geometry later on. So we can do that by selecting the whole molecule. Again, that can be done by Command M. If we have selected one atom, Command M, or we can use, for instance, Shift and left click to select in our selection window, in this case the whole molecule. If we right click and select one of these atoms, we can translate it, so we can drag it around. If we left click one atom, we can rotate the system. So in this case we want to sort of align it neatly in a way that the system can be bound easily with the unit sitting in the cell next to it. And so if we want to visualize that, we switch on the periodic view here. So it's a periodic display, and by default it will display the central unit cell and the next two units on the left and the right hand side. So in a 1D system we just see 3 units, for a 2D system we'll see 9, and for a 3D system we'll see 27. So if we want to change that behavior, you can right click and we can set the periodic range explicitly. So in this case 3 units is actually quite nice. Now this carbon atom is going to be rather far away from that carbon atom, and that is because by default we have a rather large lattice vector, and we can change that by going into Model Lattice, and we want to change the lattice vector to something maybe around 3 angstrom. If we want to measure the distance across unit cells, it will give us the shortest distance. So by default, if we select 2 atoms, it will display the shortest distance it will find, either within the specific unit cell or across the boundary conditions. So if we go from one unit cell to the next. So we shorten this lattice vector here, let's say to 2 angstrom. We see that this distance here still is 1.35 angstrom, but the distance between 2 atoms which are sitting in adjacent unit cells is getting a little bit shorter, so around 1.14 angstrom, which is too short. So let's lengthen this lattice vector a little bit, put it to 2.5, which is roughly in the right ballpark, and then we want to use that as a starting point for optimizing both the atomic coordinates within the unit cell and optimizing the lattice vector itself, i.e. the distance between the units sitting in a specific unit cell. Go back to our main panel here. We want to do geometry optimization, but by default that optimizes only the atomic coordinates, and we also want to optimize at the same time the distance between the unit cells for the infinite representation in this one dimension. So what we want to do is we want to click on this arrow here, which is going to give us more detail options, in this case on geometry optimization, and we want to say yes to lattice optimization. Now if we have a system like this is not going to take too much time with density functional base-type binding, so we can do it rather quickly. For DFTB, we can choose different models, so if you're interested in learning more about that, there's a little bit more information on that on our website, and of course our developers are happy to discuss this with you as well. For organic systems, usually what is a rather good model is third order density functional base-type binding or GFN extended type binding, and that has the advantage that it can be applied to a larger range of systems, although it hasn't been really optimized yet for periodic systems. In this case it would work fine. Let's choose DFTB3 here, and for DFTB3 we can also include dispersion. Let's take the Grimme D3 dispersion corrections here, and we need to choose a set of parameters, and let's choose dftb.org 30b31 here. So this particular combination is rather good for a large range of organic systems. Good, let's save this, and we'll save that in my ADF data. Call it polyacetylene. I'm missing an E there, but it doesn't really matter for the calculation. We'll run this, and that will bring us to the ADF jobs windows, which will show us progress. So in the last two lines here, you will see the output of the log file, and it's actually too fast to follow. It's done already. Yes, we want to read in the new coordinates, and we can see here that it has a little bit alternating bond distances here. Let's see if we can measure them. So if we select two carbon atoms, actually they have the exact same distance here. So we can see we re-guess bonds. So this bond guessing algorithm, density functional theory and density functional base-type binding, doesn't really know about bond distances. There are of course methods to estimate them. So this visualizer is trying to guess them based on atomic distances and van der Waals radii. Okay, so the system is now fully optimized, and if we have a look at the lattice vector here, we see that it has converged to something a little bit lower than 2.5 angstrom. Now this concludes our simple linear polymer builder. If you want to build something similar like that, where you have an exact one-dimensional representation of your system, you could work with different monomers, and let us know if you have any questions or problems with that. If you want to use this as an input for doing a molecular calculation, that is also an option, and usually you'd want to build a supercell. That can be done by right-clicking on this structure tool here, left-clicking, generate supercell, and we can make maybe 5 of these units come together. And now if we switch off periodic representation, now we have a unit cell which looks like this. And if we switch back to our molecular DFT code ADF, or we could have switched periodicity here, so now we have a oligomer. We can use Command E again to saturate the system. And now we could use that, for instance, for very fast UV-Vis calculations. So if we choose single point calculation here for DFTB and we want to do properties UV-Vis, and we just calculate the singlet excitations, and we save that as UV-Vis oligo acetylene, and that would be a really quick way to get a UV-Vis spectrum of part of that polymer. You can think about converging that with respect to the number of monomers. Just for full measure, let's have a look at the spectrum here. So this is our UV-Vis spectrum, and we can look at the single orbital contributions here. Good. We hope these are useful little tips. Let us know if you would like to see future tips and tricks on how to use the Graphical User Interface to the Amsterdam Modeling Suite. Thank you.